Okay, so let's chit chat about this whole buffer thing and how that plays out. What's going to happen? So here's the main thing that you, and it's tough for me to overstress this. So when you're talking about a buffered solution, you have to understand what is in that solution, okay? Versus if it's a strong acid or something like that. So if you just have a strong acid, for example, nitric acid, okay? You have a solution of nitric acid, HNO3. Here's what's going to be important. That's a strong acid. So that's existing as hydronium ions, and it's existing as nitrate ions, okay? Completely ionized, okay? The water molecules are there, we don't care about them, okay? But fundamentally, these are attracted to the water molecules. They're completely ionized, okay? Now, if you have a weak acid, like let's say acetic acid, HC2H3O2, okay? That's existing almost entirely as the molecular form, okay? You have maybe one ionized thing out of 50, yes. But the vast majority of this existing as the molecular form of the acid. Now, if you have a buffered solution of that acetic acid, you have a lot of the molecular form of the acid. Now you have a lot of the anions as well. Okay, so that's going to be huge later on. Okay, so here's a buffered solution, and there's certain criteria you have to have a buffered solution. The two criteria are that you have to have the acid, a weak acid, it doesn't work with strong acids, and you have to have the salt that has the conjugate base off of the weak acid. Okay, those are your two criteria. So the reason that you can't make a buffered solution with hydrochloric acid is that, or nitric acid, is because if you say, all right, hey, I'm going to add sodium nitrate into this, which is the conjugate base off of the nitrate. Cool, you can do that. But here's what's going to be the difference, is that if I take that nitrate and I dump in, like let's say, for example, more acid, I put in more, I add hydrochloric acid to it. What won't happen is that hydronium ion won't react with the nitrate. You're just going to make it more acidic because those hydronium ions are still going to be floating around. Now, in contrast to that, if it's a buffered solution and I add that same hydronium ions, these anions are going to act like a sponge and soak those up. So yes, you're adding hydronium ions. You could add the same number of hydronium ions to both beakers. But if it's a buffered solution, and again, understand what buffered solutions are doing. They're trying to mediate changes in pH. Okay? So if I add hydronium ions to a non-buffered solution, I'm going to drop that pH like a rock because there's nothing to absorb those hydronium ions. They're still going to exist as free-floating hydronium ions. But if I add hydronium ions to a buffered solution, the anions go, hello, sailor. They hook up, and they make HA. So the hydronium ions are still there, but they're tied up with the anions. Now, it's subtle, but it's important. If you look at pH equaling the negative log of your hydronium ion concentration, it is not the negative log of the acid. It is the negative log of the hydronium ion concentration. So I can have a bunch of hydronium ions tied up with the anions. Great. Hydronium ions are there, but they're tied up. They're not loose ions floating around. Whereas I put hydronium ions in a strong acid, they're floating around. Same hydronium ions, but completely different pHs, because this is the concentration of the free hydronium ions. not hydronium ions tied up with the anion. So you have to understand that difference. So the heart and soul of this problem is a question like, for example, that second to last one on 27. Okay, so I want to make sure everybody's cool with 27. Now, and Shannon, bless his heart, Shannon came in, he had a completely wrong reaction. I'm just saying. He randomly had the right answer, okay? Also back. But the reaction, he didn't understand what the reaction was. And I didn't notice this on some of that assignment that I just gave back, that kind of review assignment. Some of you had like the right answers, but your stoic was horrible, okay? Or you had no stoic at all. So here's my concern, is that you're going to get 1 or 2 points on an assignment that's going to make up 20% of your grade. And then you're going to get on the test, which is a huge portion of your grade, and you're not going to know how to do it. So don't sacrifice, I'll just write down the answer. It's B. Okay? How'd you get that? I don't know. Did you do the story? No. I'm just going to put down B. But then when you get on the test, and you're sitting alone at a table, and you're going, oh man, I really don't know how to do that problem. Then you're screwed. Okay? So I beg of you, resist the urge to take the easy way out. Go, hey, what'd you get? 4.85. I think your pH, yeah. What equation did you use? I'm really not sure. Just write down 4.85. Okay. Stupid. Okay? Understand the problem. Okay? That's the whole key to this. So let's talk about 27 and all of the permutations on 27. Okay. So you got acetic acid and sodium acetate. So this is what I showed you yesterday. So literally inside this beaker, what are the 2 main species that are in this beaker that you worry about?
Acetic acid and the anion.
The molecular form of the acid and the anion. Are there water molecules? Yes. Are there sodium ions because you added sodium acetate? Are there sodium ions in there? Yes. Do we care about them? No. Okay, not part of the story. They are not going to react with anything. Because the sodium ion, Na+, and again, you look at how you change pH. The only way you can alter pH is by altering the concentration of the hydronium ion. Sodium ions have no capacity, no capacity to alter the concentration of the hydronium ion. Okay? They're there, they're positively charged, they're going, whatever. Okay? I'm just going to watch what happens. I don't care what happens. Part of the story. So I don't care about the sodium ions, and I don't care about the water at this point. So on 27A, you just want to find the initial pH before you added anything. I have not, listen to me, Shannon Jones, I have not added any hydroxide.
That's why I came to
I know, and I appreciate it. Okay? Shannon and I had a great talk about Detroit Lion football and acid-base equilibrium. Okay? So on 27A, here's your reaction. That's it. There is no hydroxides. There are no hydronium ions added. This thing is just trying to find its own way in the world. Okay? This is it. There is nothing else added. Okay? I can't emphasize this. There is nothing else in there. That's it. Okay? So, here's your reaction. That's it. That's it. So, I see, here's your equilibrium. Now, technically, this needs to be molarity. But they were nice on 27 because they put 0.1 moles in 1 liter. So, since it's 0.1 moles in 1 liter, the moles and the molarity are the same thing because it's in 1 liter. Okay? But understand this. This needs to be, in this situation, because of the fact that I'm going to be dealing with Ka values, this technically needs to be molarity. Okay? Now, it's the same number of moles or molarity, but this needs to be molarity. And then you've got, what's the other one? 0.13 moles of anions. Hydronium ions start at 0. minus x, plus x, plus x. This doesn't change. This is x. This is 0.13. Now, you should be able to do this in two different scenarios. Okay? Two different scenarios. Both have their advantages in understanding how this process works. One is that you realize Ka equals your hydronium ion concentration, which is x, times your anion concentration, which is 0.13, divided by 0.10. Okay? Great. When you find x, what are you finding? The hydronium ion concentration. Because Mother Nature wants to be in equilibrium. So the advantage of this is that you realize, oh, hey, no matter what, Mother Nature has to satisfy the mathematical requirements to generate that Ka value. Okay? Because that's what Mother Nature wants. Mother Nature wants to be in equilibrium. So when you find x, you are finding the hydronium ion concentration. And then you can take the negative log of that, and then you can get your pH. Okay? So that's the deeper truth. Okay? And the advantage of that is it forces you to think through the process and go, yeah, hey, I'm trying to find that Ka value. What I'm missing is the hydronium ion. Find that, then I can take the negative log of that. Because I still want it to equal the same Ka. Now, then you have the Henderson-Hasselbeck equation, which is also advantageous. So the Henderson-Hasselbeck equation is going to be pH plus the negative log of your Ka value for acetic acid, that's 4.74. Taking the negative log, 1.8 times 10 to the negative fifth, you get 4.74. Okay? Plus the log of your anion concentration divided by the concentration of your acid. Cool. Okay? Now, the advantage of this is that when you look at that anion concentration being 1.13 and your acid concentration is 0.1, before you do any math at all, you should be able to look at that. Is your pH going to be bigger or smaller than your pKa?
Bigger.
Why?
Log of 1 over.
You're taking log of a number bigger than 1. So when you get done, you know your pH has to be bigger than 4.74. So the advantage of the Henderson-Hasselbeck equation is that it allows you to predict what's going to happen when you get done. Okay? The disadvantage is that it doesn't give you the hydronium ion concentration directly. And my fear is that you just slam numbers into this and you really don't know what the numbers are. Okay? That's my fear of the Henderson-Hasselbeck equation. So like, yeah, I got a number. You know what it means? No. I got an answer. Oh, great. But I have really no idea what the reaction is. Okay. Now, when you get to 27B, I'm going to add 0.02 moles of potassium hydroxide. Do you care about the potassium?
No.
Absolutely not. It has nothing to do with this problem. Okay? It could be sodium, potassium, lithium. Doesn't matter. What's the only thing you're going to worry about?
OH.
OH. Now, again, understand this. In this beaker, you have the molecular form of the acid, and you have a bunch of the anions. Okay? You have both. So, here's what I want you to see. If this had been a non-buffered solution, this is the non-buffered version of this problem. You're going to generate water and the anions, right? So this would be your rice line. So let's say this is 0.10, you're going to add 0.02. And the big difference here is that that anion concentration is going to start off at 0. Okay? Now, anytime you are doing anything with stoichiometry, where something is going to get consumed and something is going to get produced, what are the only two units you can work in? Moles or what are you forbidden from working in? Molarity. Okay? Because molarity just tells you the concentration. It doesn't tell you how much of it is. Okay. So if this was the non-buffered solution, you'd go minus 0.02, minus 0.02, plus 0.02, and you get 0.08 and 0.02. Non-buffered solution, okay? Slam that into the Henderson house and back, hey, you're off to the races, okay? Cool. Now, but if it's the buffered solution, which this is, it's still the exact same reaction. It's still HA plus OH yielding water in the anion. So what's the only difference now?
We start off with it minus.
You start off with anions. Okay? You start off with anion. It's not a zero value. So on this one, you're told that you have 0.02 moles. Okay, cool. That's 0.02 moles. The acid is whatever that is, 0.1. Okay? And you're adding, we're adding 0.02 of that. And the sodium acetate was 0.13. So this should be 0.13. Okay? Now, this reaction is going to go until either the acid runs out or the base runs out. Then the reaction's going to stop. What's going to run out first? Base, because that's the smallest amount, right? Oh, minus 0.02, minus 0.02, plus 0.02. Oh, when I take 0.13 plus 0.02, what do I get?
0.15.
I asked. Yeah, you get 0.15.
Oh, I thought I got it wrong.
No. You just jump in on the answer without asking. 0.08. Okay? Now you can put that into the Henderson house and make it further. Or you can go back to the Ka value. But here's what I want you to see. Is that when you add that base, it's going to react with the acid and make more anions. Okay? Now, when you get to C, now I'm going to add nitric acid. Oh, is nitric acid a strong acid? Absolutely. So again, visualize inside this beaker. You have the acid and you have the anion. I add nitric acid. I don't care about the nitrate, not part of the story. Nitrate can care less, not part of the story. What's the hydronium ion going to react with? The anion or the acid? Anion. Why? Why? But that's true. But that's not the point of the story. Why is this hydronium ion going to bond with that anion?
Well, it's bingo.
Huh?
It's bingo.
That's true.
So
That's valid.
It wants a date. To go
Why?
It comes from a strong acid.
So it comes. Hold on.
Oh dear.
The anion is the conjugate base off of a
Oh,
weak acid, so therefore it is a strong conjugate base. So that's why they want to hook up. Okay? Because if that had been hydrochloric acid and you had had a bunch of Cl in there, nothing would happen. Okay? Nothing would happen. So when you write the net ionic, and you got to do this on the assignment today, okay, you're going to live and die by net ionics. The net ionic is going to be that hydronium ion reacting with that anion, and what are you going to make? HA. Now, there's a whole bunch of things you don't care about. I don't care about the water. I don't care about the nitrates. I don't care about the sodium ions. I don't care. Not part of the story. Are they there? Yes. But I'm there to watch the Chiefs play. I could care less what's happening with Taylor Swift. Okay? She's a spectator. Don't care. I worry about what's happening like on the field of play. And this is what's happening in the field of play. So, that is the most important thing you have to understand with buffer solution. You have the acid, you have the anion. What happens when you add a strong base? What happens when you add a strong acid? Okay? That's the most important thing that you have to get. Now, when you look at your answers on 17, okay, and it's that percent of ionization, and I want you to understand the huge difference between these two. So on 17, you calculate the percentage of ionization, and again, use that 0.0075. I have no idea why they left the 5 off the end of that. So that's 0.0075. So then you're going to do it where you've added sodium butanate to it. So again, here's this trend. Just don't give the numbers. Step back. Because if you look at how you calculate percentage of ionization, it's your hydronium ion concentration divided by the concentration of the acid times 100. Right? So that's part of the story. That's page 1 of the story. Page 2 of the story is that the Ka equals the hydronium ion concentration times the anion concentration divided by the concentration of the acid. That's page 2 of the story. Okay? Page 2. So you want the same Ka value because Mother Nature wants to be in equilibrium. So if it's the non-buffered solution, this is just X and X. X squared, you have a certain hydronium ion concentration that puts you in equilibrium. Okay? So that's about 5%. Okay? So your answer to 17A is about 5%, a little bit less than that. Okay? Which means that you have a pretty substantial hydronium ion concentration. Now, here's the difference. When you get to 17B, you still generate the exact same Ka value. But now you've overloaded this thing with a bunch of anions. So what has to happen to the amount of hydronium ions?
Go down.
It's much smaller to produce the exact same Ka value. So just don't look at that and go, hey, my calculator spoke. I got 4.5% and 0.02%. Okay? Understand why that percent of ionization is so much smaller. It's because you have the same Ka value. It takes a much smaller concentration of hydronium ions. Therefore, the percent of ionization is much, much lower. Okay? All right. Cool with that. Any questions?
31. Oh yeah. Too many words.
Too many words?
Yeah, I didn't even.
Lots of words. Okay. So on 31, let's talk about that. You have to prepare a pH of 3.50 buffer. Okay? And this is what you're going to do in the lab tomorrow. Okay? This is what you got to do. So if you start with the Henderson-Hasselbeck equation, pH equals pKa plus the log of your anion concentration, we all know this story at this point. So you want to end up on 31 with a pH of 3.50. So would you want to start with a pKa of, say, 8?
No.
No, why?
Too far away.
Yeah, it's like you want to watch K-State play, but your tickets are in Lawrence. Okay? That's a long way away. So if you want to prepare a pH of around 3.5, what do you think you want your pKa to be around?
About 3.5.
Around 3.5.
Which one's that?
I don't have the faintest idea. Oh, I do, but that's a bullshit law. So, what is pKa? How are you going to find the pKa? Negative log of what? So you have to go to the back of the book and look up the Ka values of those acids. Find the one that's closest to 3.5.
It's
You can catch.
There's one problem. Too many words, remember? But no, I'm.
Did you hear that life-sucking sigh that went out of my body?
Yeah, my bad. That's on me too.
You can just feel it just go. Okay. Yeah, so what?
15C.
Huh?
15C.
15?
Yeah, part C.
Okay.
Let me get that.
So on 15, part C. So 15 part C is the same idea. 15C, you have a buffered solution, right? Because you have the acetic acid and you have sodium acetate. And you're trying to find the pH. So your reaction is just going to be HA, you need your hydronium ions and your anions, right? So there's your reaction. There's no hydroxide. There's nothing else external added to it, okay? So in this situation, because of the fact that we're going to be dealing with molarity, okay? So in this situation, because of the fact that the volumes are the same, they're both 50 milliliters. So on 15C, you have a couple of options. One is that you can find the number of millimoles by taking like 50 times 0.15 and get the number of millimoles. And then divide that by the total volume of 100 because you're mixing 50 and 50. So that concentration technically needs to be what the concentration is after they are mixed. So you could take this, you take 50 your milliliters times the 0.15 and then divide that by 100. So you're going to take 50 times 0.15 and divide that by 100. That's going to be the concentration of your acid. And then you're going to do the same thing over here. You're going to take 50 milliliters, but the anion concentration is 0.2, and then you're going to divide that by 100. Now, here's something important. Okay, everybody pay attention to this, because we're going to need to know this in the next part once we get into KSP and QSP. So, notice on this one, you're mixing two things together. You have 50 milliliters and you have 50 milliliters. This is important. You're mixing equal volumes. You always need the concentration immediately after they are mixed together. So if you mix equal volumes, you're basically doubling the volume. Does that make sense? Like we went from 50 to 100. So if you double the volume, what do you think happens to the concentration? It becomes half as much. Okay? So you really didn't even need to know that stuff. When you look at this and go, oh, we're doubling the volume, the concentration becomes half as much. So you could just use like 0.075 for your acetic acid and 0.1 for, because you're doubling the volume, so the concentrations just become half as much. Okay? But then once you get those, then you're going to go minus X, plus X, plus X. So this just becomes like 0.075. This becomes 0.10, and this becomes X. So then you could either set it up as Ka equals that X, that hydronium ion concentration, times that anion divided by the concentration of your acid, or you can slam it into the Henderson acid equation. Whatever works. Okay? All right, anything else? Once, twice. So on these problems, especially when you get into today's assignment, when there's multiple parts like A, B, C, D, make sure that the work you have is right beside that answer, okay? Don't make me chase your work. Like, don't have, like, the answer, like, here's your paper, okay? And you have the answer to 15A here, and then you have the work here, and then you have the answer to 15B right here, but the work to 15B is, like, in a completely different part, bad, okay? You keep that work right beside those answers. Got it? Good, Grant? All right. Give those handed in. So Ella, stop the camera and go to